The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
At the end of last hour, we had just gotten to the point of having developed the molecular orbital energy level diagram for the BH3 molecule, this trigonal planar entity. And I hadn't had time last hour to show you what these molecular orbitals look like in their calculated form. And so I'm going to start off today by doing that, and then we'll proceed to answer a quadrangle of questions that we can attack regarding diatomic molecules using molecular orbital theory. So I'm going to remember that the BH3 MO problem is a 7-orbital problem. And so we'll go through and just look at these 7 molecular orbitals in ascending energy from the lowest energy on up. This one is the lowest energy molecular orbital for BH3 as calculated using a modern quantum chemical package. And what you can see is that since we're indicating the phase of the wave function by color, there's only one phase to be seen. This, of course, is a characteristic property of an s orbital. Remember that. And what we've got here at the center of the molecule is the 2s orbital on boron. And in this molecular orbital theory, effectively what's happening is that 2s orbital on boron is reaching out and simultaneously overlapping with the 3 1s orbitals on each of the hydrogens. And that, the way that we've orthogonalized it and normalized it, amounts to a single molecular orbital that can, if you will, house a pair of electrons in this orbital that is simultaneously bonding between boron and the 3 hydrogens. So you have a 1 electron pair in here. 2 of the 6 electrons in the valence shell of this molecule are in this lowest lying, most tightly held, most electronegative molecular orbital. So let's look now at the next one. This is why I really need the lights down here. Moving the pointer over there is a little tricky. Okay. So you should be thinking in your mind just what was the next highest lying orbital that we had. And you'll realize that this is an orbital formed from one of the boron p orbitals and a linear combination of 2 of the hydrogen wave functions. And let's see if you can recognize it based on what we did last time. Maybe I can reorient it to help in that regard. Okay, so here is a molecular orbital that can house a pair of electrons, 1 spin up and 1 spin down, and that is simultaneously bonding from that boron to this hydrogen up here, and then there's a nodal surface here that is coincident with the nodal surfaces of the boron 2px orbital, using the same coordinate system that we were using last time. And so the wave function changes sign as you pass through the boron, and then the opposite phase lobe of the boron 2px orbital is able to overlap with these 2 hydrogens here. So if you'll remember, when I wrote down the normalization constants for this molecular orbital, we had double the coefficient on the hydrogen up here as compared with the 2 hydrogens down here, and they were opposite in sign. And that leads to real nice overlap, as you can see here. So this is BH bonding here and BH bonding down here, and it involves that boron 2px orbital. One way you can think about this molecular orbital theory is that this 2px orbital on the central atom is reaching out with its intrinsic plus-minus phase combination that is intrinsic to a 2px orbital, simultaneously reaching out and bonding with all 3 hydrogens in the only way that it can, being a 2px orbital. Okay? And so we created that linear combination with that idea in mind. And then if we go up 1 more in energy, strike that, not 1 up more in energy, but to the other orbital in the molecule that is at the same energy, then what we will find is that we're involving now the 2py orbital, and it will reach out and interact with hydrogens in the only way it can, given its intrinsic nodal properties as a 2py orbital. Remember that a 2py orbital has the xz plane as a nodal surface. And there's a hydrogen up here on that xz plane, namely the one that lies on the plus x-axis. And because it lies on the intrinsic nodal surface of this 2py orbital, it can contribute nothing to this molecular orbital. So all we're seeing up here at the top is an arbitrary sized sphere just to show the location of that nucleus, the hydrogen nucleus that is on the plus x-axis. And then here, what you see is the 2py orbital oriented along y and overlapping simultaneously with a plus 1s wave function here and a minus 1s wave function here, so that you see a beautiful bonding molecular orbital that's at the same energy as the one we just looked at. And so as you step up in energy, looking at the energy level diagram for BH3 from last time, that's what you see. We've got now 6 electrons in the molecule, 2 in this orbital and 2 each in the 2 orbitals we just looked at, that provide the 3 BH bonds that we represent in the valence bond theory as electron pair bonds. Okay? But this is a totally different way of looking at the electronic structure that is very appealing because it just takes advantage of the atomic orbital properties that you would calculate for your central atom. Now let's go up one more. The very next one, I will skip showing it to you for purposes of saving time here, but you know that the next orbital up is simply the 2pz orbital on the boron, which is our lowest unoccupied molecular orbital also, as well as being an atomic orbital in this system and responsible for the Lewis acid characteristics of this species. And one up above that, one higher in energy than the LUMO, is the orbital that I did show you last time. It's the out-of-phase combination of the boron 2s with the 3 hydrogen all with the same sign, so it's sort of a round nodal surface intersecting each of the BH bonds. And then finally, orbitals numbers 6 and 7 are the anti-bonding counterparts to the ones that I just showed you, involving borons 2px and 2py wave functions. So here's what these look like. And this one, you'll see, involves the 2px orbital. So here's our x-axis pointing up, and the blue lobe of 2px, the positive lobe here, as you can see, has squished out and down. So these pictures can be a little bit more complicated than what we're used to looking at from just sketching it out or on the board, or the qualitative pictures that you sometimes see in your textbook. But what we do find here that's the important feature is that as we go from the 1s contribution on this hydrogen over here to the positive lobe of 2px, we're going through a nodal surface. And that is anti-bonding in character. And you can see that this deformation of this lobe of the p orbital, of course, looks like a high energy type of phenomenon, and indeed it is. This is one of the highest energy, or one of the 2 highest energy orbitals in the energy level diagram for the BH3 molecule. And then similarly, here's the other lobe of the 2px orbital, the minus lobe. And as you try to go from it to the adjacent hydrogens, remember in the bonding one, we were allowing this to overlap with the same sign on the hydrogens. Now we have the opposite sign on the hydrogens, so that we have a beautiful anti-bonding node indicated here and here between the minus phase lobe of 2px and those adjacent hydrogens. So this orbital, this anti-bonding orbital, has lots of internuclear nodes that appear between nuclei and indicate that we're not getting overlap and bonding, but rather we're getting a high frequency orbital that is likewise high in energy. And finally, I will show you the counterpart to this one that involves 2py. It's a little easier to understand from inspecting it. And it also evinces the internuclear nodes that you would expect for an anti-bonding molecular orbital, and I'm orienting it so that you'll be able to understand it with reference to our coordinate system as introduced last time. And so you have the boron and the hydrogen along X up here. Here's our 2py. It's sort of bending away from these two hydrogens whose wave functions have opposite sign to the lobes that are directed into their vicinity. So you can see that we have here a nodal surface between boron and this hydrogen, where in the bonding counterpart that we looked at, we had the same sign and a nice bond. And then over here, once again, the mirror image. So this is one of our final orbitals in looking at the BH3 energy level diagram. And it's the case that if you start to put electrons into anti-bonding orbitals, they will cancel the bonding properties of the bonding counterparts. And we'll explore that in quite a bit more detail here shortly. So let me leave that up there for now and tell you what quadrangle of problems it is that I hope to answer for you today using more MO theory ideas. The first of these will be why He2 is so stable. And then, so today's lecture is predominantly devoted to diatomic molecules, and He2 will be the first of these. Let's make this an unstable. Okay? Let's do stable here in just a moment. But first, let's say next, why does O2 have unpaired electrons? Certainly, if we draw the valence bonds picture for O2 like that, it doesn't give us any indication that this diatomic molecule would have unpaired electrons. And so we're going to see how MO theory can shed some light on this issue. And then the final two questions that I will fold into one line here, given the way I'm using up space on this board, is why is N2 so stable? And CO poison. Okay, so MO theory can shed a very clear light on all of these questions. And so that's what we'll work on for the rest of the hour. In MO theory, there are a couple things you should keep in mind when trying to grasp all the subtleties of a given energy level diagram with which you may be confronted in your textbook or on an exam or just through reading papers in the Journal of the American Chemical Society, wherever you may find these. You should keep in mind that, number one, interaction is strong. That is, when atomic orbitals interact to form molecular orbitals, the AO interaction is strong. When there is good spatial overlap. Overlap is a central concept in molecular orbital theory. Okay, the idea is that if you have atoms that are far apart from each other in space, then their wave functions have dropped off exponentially and aren't interacting much, and there isn't good overlap. But when orbitals are close in space, and if their orbitals are directed in space toward one another, then there may be overlap that leads to good bonding. And also, I can echo this first part. AO interaction is strong when, and say 2, AOs are close in energy. The interacting orbitals are close in energy. Okay. When I talk about where atomic orbitals are in energy, I'm going to really want you to think about your periodic table and the properties that appear with periodicity and are organized and collated in the periodic table. We're going to be talking about properties like electronegativity as it relates to the energy. And I'll get to that a little bit on the next board, but first let's make a small MO diagram here. And this will be a diagram that we may use both for H2 or HE2. This is the simplest of all MO diagrams and one with which you should be quite familiar. We have a bonding molecular orbital at low in energy. And notice that if this is a 1s orbital over here and this is a 1s orbital over here for H2 or HE2 systems, then when these come together and bond, here's your two nuclei, and here's a probability density isosurface that I'm drawing around that shows in-phase combination of those two 1s orbitals merging with each other, giving good overlap, and the interacting AOs being of the same energy because the H2 and HE2 molecules have such symmetry. We have a good bonding orbital, and then up here we must find there to be an internuclear node in that corresponding anti-bonding orbital. And so it will look something like this. And therefore, I'm going to associate with this high-lying orbital an asterisk to indicate the anti-bonding character, the presence of this internuclear node. Okay, the change of sign as we go from one nucleus to the other, the absence of bonding character. Here we have the buildup of electron density in the internuclear region, electrons being stabilized by being held simultaneously by more than one nucleus that's positively charged. And here, the exact inverse of that, constructive interference and destructive interference in the H2 or HE2 systems. And then we can ask, well, how many electrons do we have to put into the diagram? Okay, if it's the H2 case, then to figure out the bond order, what we do is we populate the diagram according to the same kind of Aufbau principle that you would for generating the energy level diagram for an atom, and taking into account things like Hund's rule. If it's H2, we have two electrons that we can put in, and they go in here with opposing spin, like that. That's our bonding molecular orbital. So we have two bonding electrons, 0 anti-bonding electrons. Divide by 2 equals a bond order of 1. We have an HH single bond in the case of the H2 molecule. But if we have HE2, then in the HE2 system, we've got two more electrons, and the only place they can go is up here in the anti-bonding molecular orbital. So we have 2 bonding minus 2 anti-bonding over 2 is equal to 0 for a bond order of 0. And so the idea is that if two He atoms collide with each other, when they do so, their orbitals may overlap and give rise to bonding, but simultaneously you get anti-bonding and the net bond order is 0, and so He2 is not bound, but just these atoms just bounce off each other. There's no stabilization. And you can certainly understand that if we were in the middle somewhere, as we would be if we had He2 plus, missing one electron up here, then our bond order would be 1/2. Okay? So it's going to get a lot more complicated than this. But this you have to know, because this is a really nice starting point for thinking about bonding in all kinds of scenarios where you may need to consider it. And so let's look at some periodic properties. This will be with reference again to energy, and I'm interested in how some of the properties of the atoms vary as we go across the periodic table, from lithium to beryllium to boron to carbon to nitrogen to oxygen and over to fluorine. And I'll stop there. Won't worry about any more of the noble gases today. So as we go from left to right, one of the things that you know from your study of the periodic table is that electronegativity increases. This increases from left to right across the periodic table in concert with increasing Z. That is the increasing atomic number. That is the increasing number of positively charged protons in our nucleus as we go across. Each time we're adding more protons to that nucleus. The nucleus is becoming more and more positively charged as we go across. And an important consequence of that has to do with the fact that s orbitals don't have a node at the nucleus, whereas p orbitals do. Since these elements are in the so-called p block of our periodic table, well, lithium in the s block, but we will consider the properties all the way across. And the energy issue up here that I'm going to be concerned with is the energy of the atomic 2s versus 2p orbitals as we go from left to right across the periodic table, systematically adding to the number of protons in our nucleus in a way that does not affect 2s orbitals the same way that it affects 2p orbitals. It turns out that by the time we get over to fluorine, where we have essentially our most electronegative element, the 2s orbital has sunk to a very low energy. And the 2p orbital has gone down in energy as well, but just not by nearly as much. And so it's nearly an isotonic function as we go across. P is decreasing in energy in response to this increased Z, but not as much as 2s is decreasing in energy, having to do with the fact that 2s electrons see much more of the nucleus than 2p electrons do, because 2s electrons don't have a node there. So they spend a lot more time in close to the nucleus than do your 2p electrons. So this has a really important influence on that set of diatomic molecule MO theory problems that are 8 orbital problems that we call homo or heteronuclear diatomic molecules of these elements. Okay? And that has to do with the fact that in between nitrogen and oxygen, a change takes place, a fundamental change takes place in the energy level diagram. And that change that results from the atomic structure of the elements ends up with the result that the MO diagram is much easier to draw for oxygen, O2, and fluorine, F2, than it is for the earlier ones. And it's much easier to understand for O2 and F2 than it is for N2, C2, B2, BE2, Li2. Okay, so let's just see what that means. First of all, when we're going to draw an energy level diagram for a diatomic molecule, if it's a homonuclear diatomic molecule, meaning the two atoms that are going to be bonded together are the same, that means that the atomic orbitals for the contributing atoms are the same. Okay, so here on the left, what I'm drawing is, let's say, an F or an O atom. We have the 2s and the 2p, x, y, z. That's 4 of the 8 orbitals in our problem. And then over here, we have the other identical F or O atom with its 2p, x, y, and z, and 2s orbitals at exactly the same energy as for the counterpart over here. So this is another F or O atom. And then we're going to ask, how can these atomic orbitals combine to give molecular orbitals in these diatomic molecules? Okay? This is unlike the BH3 problem because there's no atom at the center of gravity of our system. But the ideas are the same. And the ideas are very much the same as what we have here for H2, where also we could make molecular orbitals despite the fact that there was no atom at the center of our system. Okay? We can pretend that there is, and we can use that pretend atom to identify what linear combinations we should make. A simpler way to do it at this point would be to say that our molecule has the 2 nuclei oriented along the z-axis, okay? And then you have x and y perpendicular to z. And so if we take this choice of coordinate system that the molecule is oriented along z, the 2 nuclei lie one on plus z, one on minus z, then we can immediately classify our atomic orbitals as being either sigma or pi with respect to the z-axis. Okay? So I'll say AO's sigma or pi with respect to z, which is the molecular axis. Okay? And remember what that means in terms of the nodal properties. If something is sigma with respect to z, that means if you view it down z, it will look like a cylinder. It'll look like a sphere, actually. It will be cylindrically symmetric about the z-axis. Okay? If something is pi, so if it's sigma, then if you're viewing down z, you see that. Okay? That could be either an s orbital or it could be a pz orbital. They would look the same if you're viewing right down z. Okay? And then pi, viewing down z, it would look like this. Okay? And that would be a px or a py orbital perpendicular to the z-axis. And this would be an s orbital or a pz orbital. So what I can say right away is that we can separate out the molecular orbitals that we're going to form from these atomic orbitals into their sigma or pi characteristics relative to the z-axis. And because we're in the O or F atom case, very far on the right-hand side of the periodic table, we have a large gap. This gap is large. We can make the approximation that this 2s orbital here, which could in principle form a sigma bond with this 2pz orbital over here, that would be an interaction looking like that, that does not occur. Because remember here I said that you get you get strong interaction when the interacting AOs are close in energy. When you're talking about these very electronegative elements, the S manifold of orbitals is very well separated in energy from the P manifold. That leads to simplicity in the case of the diagram that we're about to draw. Because we say that this interacts with this in a sigma fashion, giving rise to bonding and anti-bonding interactions that look exactly like what we've drawn over there. So I'll draw the bonding orbital here. Actually, the anti-bonding orbital here and the bonding orbital here. And I'll show the parentage of these molecular orbitals in this way. And you'll recognize that this is our in-phase combination, and this is our out-of-phase combination, analogous to the H2 problem. This is like the H2 problem built into the F2 or the O2 problem. Okay? And next, what we find is that we can also make a sigma bond by interaction of PZ with PZ. So this is going to be a nice, strong, directed bonding interaction that will look like this. You see we have overlap here in the center with a nice strong bonding interaction in the center with two PZ orbitals that are directed at each other. And this is a sigma bond because if you view that down Z, it's going to look like a round thing. It's not going to see any nodal surfaces. Okay? And then it has up here a corresponding anti-bonding orbital. Right there. I've got, so far I've got two pairwise combinations that give us two sigma bonding orbitals and two sigma star orbitals, anti-bonding orbitals. Okay? So that's pretty straightforward. And once again, I can say that we've got the H2 problem built into this energy level diagram twice, with the S interactions, with the PZ interactions. The only thing I have left is to do my PX and PY interactions. And we can make a pair of pi bonds and a pair of pi anti-bonds that corresponds to those pi bonds. So this one's pi, this one's pi star. And what do they look like? Well, they look like side-to-side bonds between pairs of p orbitals. This is just like what I showed you for the ethylene molecule. The pi bond, in fact, has this nice overlap on one side and up here on the other. There's your pi bond. And you have one of those that lies in the xz plane and one of those that lies in the yz plane. So you've got two of them, and they're at equal energy here. And then up here, what do the pi star look like? Well, the same, except we turn around one of the p orbitals, introducing a nodal surface. Like that. And we have two of those, and here's our nodal surface. Now it's an internuclear, between the nuclei, nodal surface, indicating anti-bonding character there. Okay. So that's the easy case, because S and P are very well separated. And what you can see, though, is that this interaction here, this type of interaction of a 2s on our left atom with a pz on the right atom, that might start to become important as you're over here in this part of the diagram, where S and P are pretty close together in energy. And that's what happens. In fact, and that's what happens as soon as you go to the left of oxygen and to nitrogen or anything lighter than nitrogen. Suddenly, you can't ignore interactions of S on one side with P on the other. And so I'm going to draw here the diagram that you would use, say, for N2. And for simplicity, I'm just going to draw the middle part. So this part here in the middle is that which corresponds to the molecule. So this one is what you would use for O2 or F2. And let's just go ahead and draw that diagram for the molecule. So this one would be, this set of energy levels corresponds to, for example, N2. And we have increasing energy on the vertical axis. We're going to find that we have, again, we have a sigma and a sigma star. And then the difference comes right here, where we find that as we go up in energy, we next get to our pi bonds, and then the next sigma orbital is slightly higher in energy than the pi system, rather than slightly lower in energy. And then we will encounter up here our pi star, and then finally that highest in energy sigma star. Okay? This switch, this sigma going up relative to that pi, is really a consequence of all the sigma orbitals being responsive to the value of the electronegativity of the 2s orbital of the atom. When you can really almost consider the pi system independent from the sigma. So these 4 sigma orbitals, sigma, sigma star, sigma, sigma star, I can call them 1 sigma, 2, 3, 4, just to show you that we have, in ascending order, 4 orbitals of sigma symmetry. That whole manifold, when you can start mixing a little bit of very low energy S into it, that whole manifold sinks down relative to pi. Okay, you're mixing a very, in the case over here, we're pulling down the 4 sigma orbitals relative to pi. And here, because our s orbitals are higher in energy relative to our p orbitals, they go up a little bit, and it bumps 3 sigma up over pi. And what it means is that these orbitals aren't so simple anymore. Any one of them is a linear combination of 4 atomic orbitals. So this orbital here, 1 sigma, won't look like it looks in the H2 problem anymore. This 1 sigma will have some p mixed into it. And so one way we can represent that through a simple drawing is like this. Okay. You see the difference between that sigma bonding orbital and the one up there? We've got some extra little nodes in here that are an inherent characteristic of the contribution of 2 pz orbitals into this. So this is a linear combination of the 2s and the 2 pz orbitals on the 2 atoms we have. So there are 4 orbitals, 4 atomic orbitals that go in with different coefficients to these different parts of the sigma manifold. And then up here, the other bonding orbital, we can draw it this way. And this molecular orbital, so that's this one here, 3 sigma, has diminished bonding character in between the 2 nuclei and enhanced character on the outside, the part of the p orbital that's contributing to it that points away from the other atom. And so this, while this has bonding character, it also has what we might think of as lone pair characteristics. Okay? So in MO theory, some orbitals are not that simple. They might be at the same time a little bit bonding and a little bit lone pair in character. Let's look at a couple of orbitals like that briefly. And here I've done this for the C2 molecule. So I've done the calculation for C2. So now we're over here on the left-hand side of that dividing line where S and P are a bit closer together. And I'm opening up this orbital, this one down here. It's a little more complicated than the way I drew it on the board, but what you should be able to see, if I can find my mouse here somewhere, is that think back now to the first orbital I showed you today, which was the lowest lying orbital in the BH3 molecule. You remember, no matter which way we turned it, we only saw blue, which was the positive wave function. It would look like an S orbital everywhere. It had the same sign everywhere, and you couldn't see any nodal properties. Well, that would be true also for this one down here in the case of O2 or F2, because it's not mixing in P character, because the atomic S and P orbitals are so far away in energy. But now, when they're closer in energy, this orbital down here, the S over here sees the P over here, and they mix in, and vice versa. And if I turn this around, what you're going to see are these little negative lobes here that I'm indicating that are mixing in. But this is a hugely bonding orbital still, because look at how much of the orbital is centered in the region between the nuclei. This is a very strongly bonding orbital in this system. Let's now visualize the 3 sigma. The third sigma symmetry orbital as we ascend in energy. And it will look hopefully something like what I drew here. Okay, there it is. Okay, so you see this is a sigma orbital because as we look down the z-axis it looks just round, but it's certainly got a lot of p orbital character because as we go from outside the molecule through the nucleus, we get a change in sign, and then there's overlap in here. But look, the amount of the overlap in here is small compared to the amount of this lobe out here that's got just non-bonding in character because it's pointing out into space. It's like a lone pair of electrons at the same time as it's a bonding orbital. So if this molecule actually had enough electrons to fill up through 3 sigma and no higher, then you would recognize that this molecule, this orbital that we're looking at would be the highest occupied molecular orbital, and it would be responsible for the basicity and the nucleophilicity of the molecule because any Lewis acid that came in would want to come in on the z-axis to interact with this lone pair electron density out there. Okay, so that is how our 3 sigma orbital now looks. That when we're on the left side of that red dotted line to the lighter elements. Okay, I'll leave that up there for a moment while we consider a couple of interesting points. One of the things that you'll often be asked to do is to write down the configuration. And I want to finish these 2 questions here of O2, why does it have unpaired electrons? In the case of O2, we're over on this diagram, and we have 12 electrons, 12 valence electrons. So we can go 2, 4, 6, 8, 10, and then 12 up here, 11 and 12, 2 electrons up here in the pi manifold. So we're pi star manifold. We're completely filled up through pi, and then we have a half-filled pi star with 12 electrons populating the O2 diagram. So let's represent that this way. We have our 1 sigma with 2 electrons in. We have our second sigma, which is anti-bonding, with 2 electrons. Then we have our third sigma with 2 electrons. And then as we go up in energy, the next is our first pi orbital, bonding. That accommodates 4 electrons. And then we have next our second pi-type orbital. It is anti-bonding, and it has 2 electrons in it. And then all the other orbitals are empty, so I won't indicate them. This is the configuration for the O2 molecule. That means is we come back over here, and by Hund's rule of maximum multiplicity, we have 2 spin-up electrons in the O2 molecule, with all these other orbitals down here being filled. So that configuration that I wrote down for the O2 molecule over there is a very shorthand way of representing the MO energy level diagram, because I started here at the lowest energy and I went up in energy like this. And what you can see is sigma star cancels sigma, so no bonding there. We have here 3 bonds, 3 electron pairs in bonding orbitals, sigma and 2 pi. But we have 2 electrons that are unpaired electrons responsible for the paramagnetism of the O2 molecule that cancel some of the bonding down here when we want to write that down in terms of our bond order convention. We have 6 bonding electrons minus 2 anti-bonding electrons over 2 is going to be equal to a bond order of 2. That's our bond order for O2. So while the bond order is what we expect to find based on that valence bond representation of O2 up there, what we find out is that that representation of O2 up there in the valence bond terminology wouldn't tell us that the molecule should actually have 2 electrons that are not paired in the molecule, that it should have magnetism, paramagnetism, due to the lack of pairing up of all the electrons, spin pairing in the molecule. And it has to do with this high symmetry of the O2 molecule. And it can't distort from high symmetry because it has just 2 atoms, that it has very few degrees of freedom. It can't bend or something to get those electrons to pair up. And so they're unpaired. And that's why dioxygen has unpaired electrons. And then if we go to nitrogen, the order that we write these things down in is a little different because the energy level diagram is different, because now S and P are closer together. And what we have is 1 sigma with 2 electrons, or 2 sigma star with 2 electrons. And then next we have our 1 pi with its 4 electrons. And then next we have our 3 sigma with its 2 electrons. And that's it. We have 2 less electrons in the system than we do in O2. That's N2. And our bond order now is 3. That's in accord with our Lewis structure for N2. But it's a triple bond, and it's a triple bond in a molecule that is completely nonpolar, and it's one of the strongest chemical bonds known. That triple bond is worth about 226 kilocalories per mole, and it makes N2 a very fascinating molecule, and of course it's the major constituent of our atmosphere, and it's very inert due to the stability associated with having this diagram populated up all through the bonding orbitals and then no more anti-bonding electrons present in the system. So that's pretty interesting. And given the time, I think I will leave you after the following. I just want to show you one more picture as a prelude to where I will start next time. And that has to do with what happens when the 2 atoms that are bonding are different. Okay, so let's look at the 3 sigma orbital for the carbon monoxide molecule. Okay? It would look like it does for N2. It's the same number of electrons. But look here. It's very asymmetric. And that has to do with the fact that carbon and oxygen have very different electronegativity. And so this highest occupied molecular orbital for carbon monoxide, again an 8 orbital problem, and again a 10 electron system, is one where we have a much larger coefficient on the lone pair piece that is on the carbon atom of the molecule. And I'll start off with this next time, but that's one of 2 reasons why CO is a poison. Have a nice weekend.